We start with the problem of a mass on an incline. When you start with a problem of a mass on an incline, you immediately set up a set of an XY coordinate plane with the x-axis parallel to the incline, so that all the motion will be in the x direction, and a y-axis perpendicular to the incline, so that you'll have equilibrium of all forces in the y direction. Okay? The very first thing you do after setting that up is you put your weight vector, your force of gravity, onto this coordinate system. Now the force of gravity is vertically downward. This coordinate system, you could think of starting out at a horizontal and then rotating downward 30 degrees. What happens when you rotate downward 30 degrees? Well, the y-axis, negative y-axis, rotates this way 30 degrees. So you have a 30-degree angle between the negative y-axis and the gravitational force vector. The way I've oriented it here, you have then an angle of 270 degrees plus 30 degrees, or 300 degrees, between the gravitational force vector and the positive x-axis. That is, positive x-axis, you go counterclockwise 300 degrees, you get to the gravitational force vector, and then you know that the components of your gravitational force vector are going to be whatever the gravitational force in that object is times the cosine of 30 degrees, cosine with the x-axis, and that times, I said 30 degrees, 300 degrees. Again, gravitational force times the cosine of this angle gives you this component, and gravitational force times the sine of this angle gives you the y component. That's always so. You automatically get the correct positive or negative sign when you do this, which is why I kind of rave about it. You need to do this because you need to combine this with the things that you want to do with right triangles that are good things to do in order to have the option to use the system that's more natural for a given situation. And often this 360-degree representation of your angle, the angle from the positive x-axis around to the vector, is preferable because it automatically carries the right plus and minus signs. So as long as you get the vector at the right angle with the axes, you have a very simple way of calculating and representing the components. Now, having done that, the particular problem we're dealing with, you have a block on an incline. Okay, so what other forces do you have? Well, another force that's given is an applied force. It has a magnitude that's 1/10 that of the gravitational force, and I drew it a little bigger than it really would be because I wanted to have something that didn't look like just a little smudge. So I drew it, you know, at least twice as big as it ought to be, but okay. And it's oriented 20 degrees above the horizontal in the direction that would oppose motion. Well, the natural way this thing would tend to accelerate and move would be down the incline. So opposing motion would be here. So you're 20 degrees above horizontal, and that puts you, well, the incline makes an angle of 30 degrees with horizontal. It puts you 10 degrees below the x-axis. So that puts you at 190 degrees. Now, one way or another of thinking about that, if you get used to thinking in terms of the circular angles, you get very good at it. Almost everybody in the course, at least this semester, is very good with thinking about triangles, okay, and angles. You extend that, and you get what it becomes very natural to think through these angles. So if you are thinking in this context and have been for a few days, you'll immediately see why it's 190 degrees here, and many people did. Okay, we have a frictional force, which I originally put in this direction before I looked back at my problem and realized, no, in this case, the object is not moving down the incline, it's moving up the incline. Okay, now it's not going to naturally move up the incline, something had to get it moving. And it's probably not going to be just this force because it's probably not going to be big enough, but apparently it had a shove, and now there's some residual, there's some other force that's also acting and helping it move up the incline a little bit. In any case, if it's moving up the incline, then the frictional force has to be down the incline and has to be in the direction of the incline. So there's a picture of our frictional force. And then, as always, we have a normal force. And the normal force is just the reaction of the plane to all the forces that are pushing into it. Now, the forces that are pushing into it are this component of the weight. This component of the weight doesn't, but this component does. And the component of this applied force that's actually pushing into the incline, because the incline's up at 30 degrees. This force is only pushing at 20 degrees, which means it's partially pushing into the plane, so the plane has to push back a little harder. Okay, well, the normal force is the pushback of the incline to all the forces that are tending to push into the incline at a perpendicular. So this force is going to be the equilibrant of all the other y components. Okay, well, we have that framework. Then we can start writing down equations. We have an equation for y. We know that the y forces are in equilibrium. Because, why? Because this thing is not accelerating in this direction or this direction. And acceleration is in the direction of the incline. Okay? It's not floating up off the incline. There's no force that causes it to do that. And it doesn't go down through the incline, because presumably the incline is structurally sound enough to handle whatever it is that's sliding along. Okay? So we're going to be able to write down the equations of y equilibrium, and then we're going to be able to analyze the x forces, which we then divide by the mass. Well, we actually take the resultant force and divide by the mass. Resultant net force. We divide by the mass and we get the acceleration. So we're going to do that, but we'll do that in a separate video.